Ever wondered what it really takes to make software that doesn't just look like old computer hardware running, but actually acts like it?
Yeah.
Down to the tiniest, most obscure quirks.
It sounds super niche, right?
Hmm.
But digging into that process, it's like this fascinating deep dive into the past. Technical archaeology almost.
Yeah. And it can reveal secrets that maybe even the original engineers forgot or never even documented properly.
Okay.
So today, we're pulling back the curtain on exactly that kind of work. We've been going through these beta update notes for a pretty well-known Amiga emulator.
hmm
And these notes, they aren't your typical fix, debug, added a feature kind of thing. They're incredibly detailed accounts, painstaking effort, really, to get the behavior of this, decades-old silicon exactly right.
Yeah, the level of detail is something else. Our goal today really is to unpack these technical notes, try and understand the challenges and sometimes the triumphs involved in getting what they call cycle-accurate hardware emulation.
Cycle accurate.
Okay, we're going to find out why mimicking these old chips means you have to dig down, sometimes almost to the logic gate level. And what surprising things it actually uncovers about the original hardware.
And buried in these notes, honestly, are some really wild discoveries. We'll be talking about things you just wouldn't expect,
Oh, yeah.
like how a keyboard's own little brain, its microcontroller, could accidentally reset the whole computer,
Great. Who'd think?
or these tiny, almost imperceptible ways pixel timing differs between chip revisions, and the clever, really low-level tricks needed just to draw a line on the screen accurately and quickly while still making the emulator, run okay on your modern PC.
It's a real balancing act.
Okay, so let's start at the core then. This challenge of emulating complex vintage hardware, like the Amiga's custom chipset.
Right. So the first thing to get is that it's not just about making the software run fast on a modern machine. I mean, that's part of it, obviously. But the real difficulty, especially if you want to get those old demos, the really tricky ones, or certain classic games working perfectly, it's all about timing.
Timing.
Exactly. Vintage software, especially the stuff that really pushed the hardware, it didn't just use the Amiga's features. It often relied on the exact timing of operations, down to like individual clock cycles.
Wow. Okay, so super precise.
Super precise. And these beta notes really hammer that home. They talk very explicitly about removing old custom chipset emulation hacks.
Hacks, like shortcuts.
Yeah, basically shortcuts. Things that got stuff working, most of the time for most software. But they weren't truly accurate.
Right.
And now they're replacing them with, and this is a quote, new code, which is much simpler and easier to understand, works more closely like real HW.
Okay, simpler, but more like the real thing. How?
Well, here's the key bit. This new code, it's based on original schematics for the Alice chip, one of the later custom chips. And it emulates some signals in almost logic gate level.
Logic gate level. That sounds intense. Why go down that deep?
Great question. Think of it like this. The old hacks were sort of simulating the final result of what the chips did.
Okay.
The new code is trying to simulate the machine itself. The actual process, the signals interacting. It's necessary because sometimes old programs relied on these tiny, maybe undocumented timing differences or side effects.
Ah, things that only happen if the internal gears mesh just right.
Exactly. It's about replicating the process, not just the final picture on the screen.
And you see that commitment to replicating the real machine, like all through these updates, right?
Absolutely.
Yeah.
They mentioned separating the emulation of Agnes and Denise, two critical custom chips. Agnes handles memory, DMA, the copper, blitter. Denise handles the actual video output.
Right.
And the data transfer between them. It now happens over an emulated external RGA bus, just like the real thing.
So simulating the wires between the chips, essentially.
Pretty much, and keeping them in sync. They're using, quote, strobe registers used for chip synchronization, like on real HW. No more shortcuts.
No more shortcuts.
Okay.
It feels like they're really rebuilding the connections, the whole system structure.
That's exactly it. And that extends to DMA, direct memory access.
That's how the custom chips grab data without needing the main CPU all the time?
Exactly. Agnes does a lot of that. The
Uh-huh.
updates talk about accurately emulating the hardwired DMA slot selection,
Yeah.
shift register chain, and crucially, DMA conflicts.
Conflicts, like when two chips want memory at the same time.
Precisely. What happens then? The notes emphasize this is now done without hacks. And getting DMA timing right is just It's absolutely critical
Why is that so vital?
because DMA activity is constantly interwoven with everything else the custom chips are doing. It affects the CPU getting access to memory. It affects the copper running its display list. It affects the blitter doing its graphics work. If the DMA isn't timed perfectly, the whole rhythm of the machine is off.
And software that expects that specific rhythm just breaks.
Breaks, glitches, crashes. Yeah.
Yeah.
So that DMA accuracy is fundamental.
Okay, so speaking of rhythm and timing, you mentioned display emulation. These updates seem heavily focused on that, getting it cycle accurate.
Massively. It's a huge part of it. Getting the timing of things like horizontal and vertical blanking and sync start end, sync equalization pulses, all that stuff, absolutely perfect, down to the individual cycle.
Right.
It supports mixing different ways the Amiga could set up its display modes, hardwired versus program.
Yeah.
And yes, that sync generator part, again, they describe it as being almost logic gate level emulated.
Okay, hold on. Blanking, sync pulses. For someone maybe not depth into old monitor signals, what are those and why does getting their timing that precise matter so much?
Good point. Think of an old CRT TV drawing the picture. The beam scans across, draws a line of pixels, then it has to quickly shut off that horizontal blanking and zip back to the start of the next line.
Okay.
Does that line? Blanks, zips back. When it finishes the whole screen, it needs a longer blanking period, vertical blanking, to get all the way back to the top left corner.
Right.
The sync pulses HSYNC for horizontal, VSYNC for vertical. CSYNC is composite. They're like the timing signals, the drum beat, telling the monitor exactly when to blank, when to move the beam, when to start drawing again.
And old Amiga software messed with this.
Oh, absolutely. The copper chip, this coprocessor, could change display settings, colors, sprite positions, mid-frame, even mid-scan line by reacting to the beam position. Demos especially use this to create effects that seemed impossible. Changing resolutions on the fly, drawing way outside the normal screen borders.
Ah, okay. So if the emulator's sync timing is even slightly off.
Those copper tricks just fall apart. You get glitches, shimmering, effects just don't work, or the whole display sync is lost. Getting it logic gate level accurate means those really complex, often undocumented tricks should work just like they did on the real thing.
And this level of accuracy, it enables things the source actually calls ROS, special screen modes. Sounds intriguing.
Yeah, it does. Because registers like VPOSW and VHPOSW, which control where the display starts drawing vertically and horizontally, can now be changed on the fly, effectively. The notes say, all old limits are gone.
What kind of limits? What can you do?
Well, they give examples like repeating the same vertical line over and over to fill the screen, or disabling the normal hardware, blanking entirely.
Just drawing right into the borders.
Exactly, which allows for much wider displays than standard PL or NTSC, potentially. Very similar to tricks people did on the Commodore 64, actually, but using the Amiga's architecture.
That sounds incredibly flexible, but also really complex to emulate correctly.
It is. And here's another detail showing that complexity. The notes mention separating the virtual and the real Agnes, or Alice horizontal and vertical counters.
These are the counters tracking where the beam is on screen.
Right. And separating them means the display emulation works correctly, even if software messes with Agnes's internal counters directly. Moves them backwards or forwards or anywhere, unlimited times per line and order field. Imagine trying to track that consistently.
Wow. Okay. It makes you wonder about other things, like how does it detect interlacing then, if it's not just flipping a hardware bit?
Good question. On a real display, interlacing isn't just a simple flag. The monitor looks for a specific pattern in the ESYNC signal timing over several fields, comparing odd and even fields.
And the emulator does that now.
Yep. Instead of just checking hardware bits like LOF or lace, it detects interlace by checking the VSYNC start position relative to H center over the last 4 fields, just like real displays.
So it won't mistake a random glitch for genuine interlacing.
Exactly. It makes interlace detection much more robust and realistic.
And graphically.
Yeah.
Any other details?
Yeah, there's full AGA high resters granularity support now. That's for precise pixel placement in the higher resolutions. And they've even emulated these previously unused ECS Agnesaga ESS bit plane and Sprite DMA slots.
Unused slots. Why bother?
Well, the notes jokingly call it a useless feature, but they include it because even if standard software never touched them, those DMA slots exist on the chip.
Ah, and they could still potentially interfere with other things.
Precisely. They can steal cycles from copper, blitter, and CPU if some weird program did try to use them. So for perfect accuracy, even the useless bits have to be there.
Okay, let's shift gears a bit. Another critical piece. The blitter. the graphics workhorse.
Right, the block image transfer. Used heavily for moving graphics data, filling areas, drawing lines, handling sprites, all that stuff. The notes state the blitter channel sequencer is now 100% accurate.
100% accurate sequencer. What does that mean in practice?
It means the order in which the blitter fetches data from memory, channels A, B, C, processes it using Boolean logic, the min terms, and writes the result back, channel D, now precisely matches the real hardware's internal state machine.
Okay.
They do mention that the timing of individual micro-operations within the blitter is still being refined, but the overall sequence and interaction of its different parts is now spot on. This includes how it handles enabling channels, fill modes, descending order, min-term changes mid-operation.
And there was something about a previously unknown condition.
Yes. This is fascinating. It relates to the blitter's block mode, specifically the D-channel scheduler logic. It now matches real hardware, but doing so uncovered this weird behavior.
What happened?
Apparently, if the blitter is set up in a specific way, with multiple bits set in the scheduler, it's possible for a second final D, writing the final result to memory, to happen after the blit has technically finished according to its size register.
Wait, a second right after it thinks it's done? That sounds like a bug in the original chip.
Could be. Or just a very specific, low-level side effect of the internal logic that maybe wasn't documented or expected, but, for cycle-accurate emulation.
Doesn't matter if it was a bug or intended if the real hardware does it.
The emulator has to do it, too. That's the goal. Absolute fidelity.
And this accuracy level means handling some tricky interactions, too, right?
Oh, yeah. The emulation now correctly handles situations where, say, the main blitter control register, BLTCON0, gets modified while a blit is in progress, especially if multiple channels are active.
That sounds like asking for trouble.
It is. And high-level emulation would almost certainly get that wrong. Or cases where you write to the blitter's address pointers or its modular registers immediately before a DMA transfer is supposed to happen for that same channel.
Race conditions, basically.
Exactly. Timing-sensitive race conditions that can cause subtle glitches or even crashes in old software that maybe accidentally did these things.
And even the timing of the flag that says the blitter is done.
Yep, the BLTZS arrow bit. The notes mention its timing is now accurate. It gets set when the blitter gets the next free cycle after BLTZSY right, and the timing matches the BLTBUSY bit on the very first Amiga, the A1000. It's that level of minute detail.
Incredible. Now, okay, here's a section that really blew my mind with the level of detail, and it comes with a great little story, the keyboard.
Yes, the keyboard emulation. This is a fantastic example.
The notes just announce optional hardware-level keyboard emulation, like it's a small thing.
Right, but the origin story is classic. The developer was doing some other unrelated low-level test, a ROS-TM test as they call it, and it accidentally messed up the keyboard communication, the handshake sequence, on a real Amiga 500.
Oops.
Exactly. But investigating why that happened led them down this rabbit hole, and they realized that simple high-level simulation just saying key X was pressed couldn't replicate the subtle timing issues and side effects.
So they decided to emulate the keyboard's own hardware.
Precisely.
Yeah.
Not just simulating the result of the key press, but simulating the actual microcontroller inside the keyboard itself.
There's a microcontroller in the keyboard.
Oh, yeah. Amiga keyboards had their own little 8-bit brain. The emulation actually covers 3 different types used over the Amiga's lifespan, based on different CPU families, 6502, 6800, and 8048, each with its own ROM code and slightly different behaviors.
Wow. So how does that work in the emulator?
Well, when you press a key on your modern PC keyboard, the emulator translates that into a signal on a simulated keyboard matrix. Then the emulated microcontroller code reads the simulated matrix, processes it just like the real chip would, figures out the key code, and then sends that code serially to CIA serial port.
So it mimics the exact communication path and timing.
Exactly like on real hardware. It's simulating the entire process from the keyboard's perspective.
And the payoff for all this complexity, what does it enable?
Accurate side effects. Things the notes list like reset warning, possible lack of N-key rollover, and other side effects if programs do bad things with key handshake.
So if old software poked the keyboard controller weirdly?
The emulator now reacts just like the real hardware would have, quirks and all.
And the best example they give is this caps lock flashing thing.
Oh, it's perfect. Some really intense old demos like Odyssey or Alcatraz apparently flash the caps lock light. Why? Because the demo code is just hammering the keyboard interface, floods the poor MCU with a huge amount of handshake pulses.
Overloading the keyboard's brain.
Totally. It generates tons of interrupts, the little microcontroller gets overwhelmed, and eventually its internal Watchdog timer resets the CPU.
The keyboard MCU resets itself.
Yes, and the tiny bit of code that runs immediately after reset on that specific MCU happens to include flashing the caps lock LED. It's purely a side effect of pushing the hardware way past its intended limits.
That's amazing. It wasn't even intentional by the demo coders, maybe.
Maybe not initially, perhaps they just stumbled upon it. And they even note that this trick doesn't work on keyboards with a different microcontroller, the D8039 HLC, because that one does not have Watchdog timer. The emulation correctly handles these chip variations.
Incredible detail. And then there's the A1200 keyboard part.
Right. Get this. The microcontroller used in many A1200 keyboards, a 68HC05C variant, is apparently designed so that when its Watchdog timer resets the keyboard MCU, it also sends a signal out that resets whole Amiga.
The keyboard resetting the entire computer.
Yep. A keyboard error can literally reboot your machine on a real A1200. And now, thanks to this hardware-level emulation, it does in the emulator too.
That anecdote just perfectly shows why this deep emulation matters. It uncovers and replicates these completely surprising real-world hardware behaviors. Stuff no one would design, but that happened anyway.
Exactly. Things high-level emulation would never, ever catch.
Okay, but doing all this, cycle-by-cycle simulation, logic gates, keyboard MCUs, it sounds like it would absolutely murder performance on a modern PC. Let's talk about speed.
Yeah, performance is definitely the other side of the accuracy coin. And the beta notes really show this constant tension, this journey.
How so?
Well, early on, Beta 1 flat out says this version is slower, especially in fast CPU modes, at least for now. Achieving that initial accuracy came at a cost.
Right.
But then you see this progression. Later notes say things like WB native mode performance restored in B8, improved even more in B10, and then a big one. CE cycle exact mode performance greatly improved in B13, now faster than 5.3.1, an older version.
So they found ways to optimize after getting the accuracy right.
Exactly. The developers are always balancing that absolute simulation fidelity with the need for the emulator to actually run at a usable speed. It's a constant optimization effort.
What kind of optimizations did they introduce?
Well, for modes where you don't need perfect cycle exact timing, maybe just running Workbench or less demanding software, they introduced a clever trick called line-based emulation around beta 7 or 8.
Line-based? How does that help?
It means for parts of the screen or even whole frames that aren't doing anything complex, like scan lines that are just empty border or part of the vertical blanking area, or maybe sections of the screen where the graphics haven't changed since the last frame and there's no copper or sprite activity.
Okay.
The emulator can basically skip the detailed cycle-by-cycle work for those lines. It knows nothing significant happened there. This makes static screens, like the Workbench desktop, much, much faster to emulate.
Ah, smart. Only do the heavy lifting where needed.
Precisely. And a later optimization, in Beta 10, took this a step further. If the display parameters for a line haven't changed, like resolution, colors per line, etc., but the actual content has changed, maybe a scrolling background or moving text, it can draw those lines directly from chip RAM, bypassing DMA emulation using quick line-based mode. It avoids the full DMA simulation for that line, grabbing the pixel data directly. Still accurate enough for many scenarios, but much faster than full simulation when the screen is dynamic.
Okay, those sound like good incremental improvements. Was there a bigger leap?
Yes, the biggest performance jump seems to have come with multi-threading, specifically for the Denise and Lisa chips, the display output chips. This was in Beta 13.
How did multi-threading help? Weren't things too tightly coupled?
That's where the new architecture paid off, because they separated the Agnes logic, generating display data, from the Denise logic, outputting pixels, using that line-based RGA buffer we talked about earlier.
Right, the emulated bus.
Yeah. It meant the Denise processing became, as the notes say, almost fully fire and forget. Once Agnes prepared a line's worth of data, Denise could process it fairly independently.
Ah, so you can run Denise on a separate CPU core.
Exactly. They could put the Denise processing into a separate thread.
Oh.
And the result, the notes triumphantly declare, finally, faster than older versions, they could leverage modern multi-core CPUs much more effectively.
But there are always trade-offs with performance, right?
Always. The notes mention that if you enable certain advanced features, things like emulating DisplayPort adapters for modern monitors or Genlock for video overlay, or even the light pen, enabling those disables non-CE border bit plane optimizations, you need the full cycle-by-cycle accuracy for those features to work correctly, even if it means lower performance.
Makes sense. What about things like visual filters, scaling, smoothing?
Interestingly, they removed all software filters around Beta 1314.17. The reason given was that they don't fit well with the new rendering path, which aims to draw directly to a texture on the GPU for maximum fidelity first. Filters might come back later, but the priority was raw accuracy.
And the CPU requirement itself tells a story too, doesn't it?
It does. Initially, in Beta 1, they bumped the requirement up significantly, needing AVX2 support, which means roughly CPUs from 2015 or later. They called it an arbitrary decision to cut off 2 old CPUs for now.
A bold move.
Yeah, maybe focusing on getting it right on modern hardware first. But as the optimizations kicked in, they were able to lower it back down considerably to SSE2 support by Beta 11.
Which covers much older CPUs.
Right. The goal became making this new, highly accurate version perform comparably to the older, less accurate versions, even on less powerful, older machines. That's a huge achievement.
Okay, so accuracy means digging into all these tiny timing details, edge cases, corner cases.
Oh, absolutely. The source notes are just full of examples that seem incredibly minor, but they matter for true cycle-exact compatibility.
Like what?
Things like the exact cycle timing. When BPL1 DAT, that's the register providing data for the bitplane graphics, is read, it differs slightly between the older OCS-ECS chips and the later AGA chips.
It's tiny.
Or minute delays that happen if you change display control registers like BPLCON0 right in the middle of scan line, and how those delays vary with different Denise chip revisions. Even the copper's jump instruction, COPJMP, they found its timing was off by 1 CCK, one fundamental color clock cycle in older emulation.
Like fractions of a microsecond differences.
Yeah, stuff that only software relying on very specific cycle counting would ever notice or be affected by. But if you want that software to run perfectly, you need to get it right.
And NTSC modes, the North American standard, had their own special quirks too.
They definitely did. Accurate emulation of certain register bits like stronglong and LOL, which control pixel width, causes a subtle Loors pixel-wide horizontal shift in NTSC modes. And the behavior of stronglong actually changed between chip versions.
How so?
On the A1000 and OCSCS chips, it caused a kind of sawtooth artifact at the right edge of the screen under certain conditions. On AGA chips, it changed, causing an alternating doubled Loors, pixel-missing Loors pixel pattern instead.
Different glitches depending on the chip revision.
Exactly. And the notes even include this exasperated comment about AGA. Annoying Shrez pixel offsets here and there are. You can feel the developer's pain trying to replicate these subtle hardware flaws perfectly.
And there was one particular glitch they called nasty.
Yes, the right edge horizontal scrolling glitch. This one's really interesting because it's not actually an emulator bug. It's caused by a genuine chipset limitation.
A flaw in the original Amiga hardware.
Sort of. It's how the hardware handles timing right at the very end of a scan line, in the right overscan area. It technically overlaps with the timing for the start of the next line in a weird way.
Okay. And this causes a visible problem.
Yes, specifically during fine horizontal scrolling. You get a visual glitch or tearing right at the extreme right edge of the display. It's ugly.
So how does the emulator handle this hardware flaw?
This is the fascinating part. In the accurate, cycle-exact emulation modes, it's emulated correctly, meaning the emulator shows the glitch, just like real hardware.
It replicates the flaw perfectly.
Yes, but interestingly, the notes say that in the fast CPU modes, the less accurate, performance-focused modes, the glitch is actually fixed.
They remove the glitch in the faster mode.
As a pragmatic choice, yeah. Because, as they say, is normally rarely visible because it looks very ugly. So perfect accuracy means showing the ugly hardware flaw. Better performance mode gives you a cleaner, albeit less authentic, picture in that specific scenario. It's a really interesting trade-off.
That is interesting. Beyond display quirks, they also added emulation for some extra hardware.
Yeah, showing the commitment to the broader ecosystem. Things like emulating the Ripilio ID controller, which was a third-party add-on in Beta 14. And even a specific, quite rare 512K RAM expansion for the very first Amiga 1000, the WOM expansion, in Beta 15.
Going after the obscure stuff, too.
Definitely. And you get a sense of the detail they're tracking just from the debugger improvements mentioned throughout the notes.
What kind of debugging tools?
Things like a DMA debugger that can show activity per scan line, or even virtual scan line. Tools to dump the complete internal state of all the custom chips, Denise, Lisa, Agnes, Alice. Showing the exact cycle counts for blitter operations or bitplane memory accesses. A detailed dump of the CIA chips showing disk status, serial port activity, even the state of the joystick fire buttons, tracing CPU accesses to the Kickstart ROM.
Wow. These aren't just tools for emulator users, are they?
No, these are essential tools for the developers themselves to verify that their super detailed cycle-accurate code is actually behaving precisely like the real hardware, step by tiny step.
Okay, so we've gone really deep into cycles, logic gates, microcontrollers, display timing, keyboard weirdness. After all that, what's the big picture? The so what? Why does all this incredibly detailed, sometimes frankly mind-boggling low-level stuff actually matter to someone just wanting to run an old game or demo?
Yeah, it's a fair question. And the answer ultimately is compatibility. All this incredibly painstaking effort, it isn't just, an academic exercise in recreating old silicon.
Right.
It is absolutely necessary if you want the emulator to be compatible with, as the notes put it, all usual badly coded demos.
Huh. Badly coded or just pushing the limits?
Probably a bit of both. But also any other vintage software that used the Amiga hardware in really unconventional ways, or relied on that super precise timing, or maybe even stumbled upon those subtle undocumented side effects that simpler high-level emulation would just completely miss.
So it's about fidelity making things work correctly.
Exactly. The whole goal here is fidelity. Getting these previously unknown conditions right, nailing these tiny timing differences down to fractions of a clock cycle. It means the emulator behaves more and more like the real hardware, flaws included sometimes.
And that's what makes the obscure software, the tricky demos, the games that pushed boundaries actually run correctly when maybe they failed or glitched out or crashed in older, less accurate emulators.
Precisely. As the notes imply for some features, emulating things that are practically impossible to emulate accurately and high level really requires this deep, low-level, cycle-by-cycle, sometimes even logic gate-level approach. There's just no other way to capture that behavior.
It really highlights that constant push and pull we talked about, the journey you see in these beta notes. Balancing that desire for a simulation so perfect, it even includes hardware quirks.
Against the practical need to get good, usable performance on modern computers that are architecturally completely different from the original Amiga.
Yeah. And it just underscores the sheer effort involved. This isn't trivial work.
Not at all. Reaching this level of detail takes incredibly dedicated work. It means, reverse engineering original ROM code, studying old schematics if they're available, writing and running specific custom diagnostic tests on actual Amiga hardware.
Like those raw, special cycle-accurate CPU SOP synced tests mentioned.
Exactly. Tests designed purely to probe these minute timing behaviors. And sometimes it even means getting people to dump the contents or behavior of rare hardware components.
Yeah.
It's absolutely a form of technical archaeology, resurrecting the digital past one clock cycle at a time.
Wow, we've really peeled back some layers today, I think, on what goes into accurately emulating vintage hardware like the Amiga. It's this incredibly complex dance of chips and signals and clock cycles that makes a system like that tick, often in ways that, maybe the original users or even many programmers back then didn't fully grasp.
Absolutely. And it's this ongoing process of discovery and reconstruction. You read through these technical updates, and they're not just about emulator improvements. They're revealing hidden details, hidden intricacies, sometimes completely unexpected behaviors of the original hardware itself, decades after it was designed and sold.
Which leads to a final thought, maybe. Consider this. These Amiga machines, they were used heavily for years, programmed extensively, documented, yet reverse engineering them now, decades later, is still uncovering previously unknown behaviors, these conditions that actually matter for compatibility with the most demanding software.
Makes you wonder, doesn't it?
It really does. What other secrets might old hardware from that era, whether it's, a different computer, an old game console, maybe early industrial controllers, whatever, what secrets might they still be holding, just waiting for someone to dig deep enough, cycle by cycle, to finally find them?